Hello, today we're going to go over Module 2 practice test. My tips for you would be to make sure you've completed all of your lessons in Module 2 and then to try to solve these problems on your own before I give the answer. I may be moving kind of quickly, but that's because this is a video. So if you need it to be paused or rewind, you can go ahead and do that. So let's jump straight into it. Use your graphing calculator to evaluate. The biggest tip with this one that I have is that when you are using your graphing calculator, make sure to use parentheses. So you want to put parentheses around your base and around your exponent when you graph this. When we graph, here's what we get. And as you can see, as x gets larger, we're approaching a horizontal asymptote, and it's getting closer and closer to 1. So our answer here would simply be 1. On our next one, they want us to evaluate the limit as x approaches a. Now, if I were to directly substitute the a into our denominator, we could see that this would give us an undefined answer. So whenever you're going to solve something algebraically, make sure you simplify first before determining and saying, oh, well, it's undefined, so therefore the limit must not exist. Before you determine that, make sure you do everything that you can to simplify the problem. So in this case, our first step is going to be to rationalize the denominator. So we're going to go ahead and multiply by the conjugate. And when I do that, when I multiply by the conjugate, here's what we get. Next, let's go ahead and simplify that. So in our denominator, the whole purpose of multiplying by the conjugate is to get rid of our square root. So that's what we're left with. Now we can see that in the numerator, what's in the denominator and what's this factor in the numerator, they're very, very similar. So the only difference is the signs. So I'm going to force these two guys to be exactly the same by taking out a negative. And when I take out a negative, this guy's going to turn negative and this guy will turn positive. And now we have the same factors in the numerator and the denominator. So I can cancel. So we've simplified as far as we can go. So our last step is just to go ahead and take the limit. So I have the limit as x approaches a, then I have my negative symbol on the outside, the square root, and I'm going to go ahead and plug in my a for my x, so a plus the square root of a, now those look like 9s, but they're a's, is going to equal negative, when I add these two together, I get 2 square root of a. For this one, we're going to go ahead and find the limit as x approaches 0. Again, if we were to go ahead and directly substitute into this guy, we'd get undefined in our denominator. We can't really do a lot algebraically here, not yet at least. You will be able to do something later on within the course. So right now, the tools that we have is graphically. But if we graph this, we can see it looks like a hot mess. So we can't really tell our answer there. The next thing we could possibly do is go ahead and do a numerical graph or a table. And what I want is numbers getting closer and closer to 0 from the left, so numbers lower than 0 and numbers greater than 0. Now remember that a limit is as x approaches the value. It does not necessarily have to equal the value, so it's okay that at 0 it's undefined. But we can see that from the left and from the right, our limit approaches 3. So it's approaching 3 from both sides. This one says if the limit as x approaches 0 is equal to 2, and the limit as x approaches 0 is equal to 6, then find the limit as x approaches 0 of f of x plus g of x. And really what we're just using is our property of limits. So they tell me f of x is 2, g of x is 6, and then we're going to square all of that. So 8 on the inside squared would be 64. Evaluate the limit as x approaches 0. Again, when I plug this one in, right away I get undefined. And there's not much we can do algebraically. We can't simplify this any further. So another thing you can do is graph it. And when we graph it, we can see that the limit as x approaches 0 from the left and from the right approach two different values. So in this case, it truly is or does not exist. The limit in this case does not exist because from the left and the right, we approach two different values as x approaches 0. Evaluate the limit as x approaches 4. Always, first step is to try to simplify this as much as possible. So let's start with the numerator. We have two fractions in the numerator, so we're going to work and we're going to combine these two fractions by finding a common denominator. So my common denominator is 4x. And when I combined my numerator, here's my new fraction. We have 4 minus x divided by 4x divided by x minus 4. And that kind of looks like a really ugly fraction. So we're going to go ahead and use division of fractions. We're going to keep the first numerator. So we're going to keep that. We're going to change our division symbol to multiplication. And we're going to flip the denominator. Now again, just like we did before, these two factors are almost exactly the same. The only difference between these two factors is their signs. So I'm just going to change one of them by taking out a negative. And when I take out a negative, it switches everybody's sign on the inside. So we're left with, these guys will now cancel. And we're left with negative 1 over 4x. And now we can go ahead and plug in the limit as x approaches 4. So we get negative 1/16. Evaluate the limit as x approaches 4x divided by 5x. For this one, we're going to be needing to use the identity of sine x divided by x equals 1. So what this is saying is that whatever we have the quantity of sine divided by that same quantity equals 1. So we need to force these two guys to be exactly the same. So I'm going to go ahead and do some algebra here. And in the denominator, I need it to be 4x. So we're going to multiply by 4/5 in my denominator. Okay, and here's what that does. It's going to end up canceling my 5's and leaving me with 4x in the denominator. But what I do to the denominator, I have to do to the numerator. So let's clean this up. Here's what we're left with. We're left with sine 4x divided by 4x times 4/5. Now, because of the property, we know that this here is just equal to 1. So we would say 1 times 4/5. So my final answer would just be 4/5. You could also graph that, and you would see that the limit as x approaches 0 of this function would give me 4/5. If f is continuous, if f is a continuous function with odd symmetry, and the limit as x approaches negative infinity is equal to negative 5, which of the following statements must be true? For this one, I went ahead and drew a picture. Odd symmetry is a graph that has symmetry with the origin. And then I went ahead and included this limit. The limit as x approaches negative infinity is equal to negative 5. Here that is. Okay, and then I took these three statements and I kind of just saw, do they apply? So if I go to negative infinity and I get my answer to be negative 5, it means I can't go past that line. So there has to be a horizontal asymptote there. And if we had odd symmetry, that means in the top, there also has to be a horizontal asymptote. Now, if it's a continuous function, we know that there's no vertical asymptotes. So therefore, we have y equals 5 and y equals negative 5 are horizontal asymptotes. So in this case, all of my statements are true. What is a horizontal asymptote of the function? There are 3 rules for this. And so if you haven't remembered them, if the numerator has a higher degree, then there is no horizontal asymptote. If the denominator has a higher degree, then our horizontal asymptote is 0. And if the degrees are the same, then we divide their leading coefficients. So what we care about really is the leading coefficient here. So we would say the square root of x squared divided by x. And I'm going to simplify that. Well, the square root of x squared is just x divided by x, which means they have the same degree. So we would just divide their leading coefficient. And in this case, it's just 1. Now you have to be careful with this because we have x squared. So if I were to plug in a -1, it would yield the same answer as if I were to plug in a 1 because of the squared. So in this case, my horizontal asymptote would not only just be 1, but -1 as well. Find the limit as x approaches infinity. The same rules apply here as horizontal asymptotes. So we would look to the leading coefficients. We see that the numerator has a higher degree. So therefore, my limit here would be infinity. If the denominator would have had a higher degree, then our limit would be 0. And if they would have tied, we would just divide their leading coefficients. Another tip is if either one of these leading coefficients has a negative in front of it, even if it doesn't win, so if either one, if let's say this guy had a negative, then our final answer would be negative infinity versus positive infinity. In this case, it says the limit as x approaches 2. Now, if I were to plug that right in, I don't get undefined. So therefore, I'm just going to jump straight into that. We're going to plug this right in. So we'll have 2, and then we have the square root of 2 squared plus 4. So we'd get 2 square root of 8. And although that's not an incorrect answer, it's not the simplest form. So I'm going to go ahead and clean that up. So in our denominator, we can rewrite the 8 as 4 times 2. And then the square root of 4 is just 2. So we'll have 2 square root of 2. And then we can simplify these 2's. So we would get, these would cancel, 1 over the square root of 2. Which of the following are the equations of the horizontal and vertical asymptotes of the graph? Well, for the vertical asymptote, we're just going to take the denominator and set it equal to 0. Okay, so and I'm going to actually simplify this guy a little bit as well. So since we have an x and an x, I'm going to rewrite the equation to be 1 over x squared minus 4. And all I did was simplify because they both had an x in common. So now I'm going to set the denominator equal to 0 in order to solve this for vertical asymptotes. I can factor that denominator into x plus 2, x minus 2. And when I set each of those factors equal to 0, I would get that my vertical asymptote, so my VA, would equal to 2 and -2. For the horizontal asymptotes, we compare the leading terms. So in this case, okay, our leading coefficient is in the denominator. So therefore, my horizontal asymptote would be y equals 0. Evaluate the limit as x approaches 1. Now, what we want to know for limits is to determine if the limit from the left and the limit from the right equal the same thing. So in this case, x is less than 1. This is technically our left side of our graph. So this would be numbers less than 1. Over here, x is greater than 1. This would be numbers on our right side of our graph. And again, we don't really care about what happens when x equals 1. All we care about is as we approach 1. So when I plug in a 1 to my top equation, I get it equals 6. And when I plug in a 1 into my bottom equation, I get that equals 3. So therefore, the limit from the left and the limit from the right do not equal the same thing. So this limit does not exist. Because in order for a limit to exist, the left and the right have to equal the same thing. Where is the discontinuities? Discontinuities, think denominator. So in this case, I'm going to go ahead and factor the denominator. So we're left with x minus 4 and x minus 5. These two factors would cancel. So I have a removable, because they canceled, removable discontinuity at x equals 4. And then because I was not able to cancel x minus 5, non-removable, I'm just going to put non, and I'm going to put the letter R for non-removable at x equals 5, because I was not physically able to remove this factor. Which of the following are continuous for all real values of x? In this case, you can graph these, or you can think of plugging in a 0, because 0 would cause our function to be undefined at that location. So if I were to plug in a 0 to this first equation, no matter if I plug in a 0, I would still add a 1, so I would get a 1 in the denominator. Or if I plug in a negative 1 here, it would still give me positive 1. So no matter what number I plug in for this x, it was never going to give me an undefined in the denominator. So this one would be continuous. Now, if I plug in a 0 here, I would get undefined in my denominator. So that would not be. And if I plug in a 0 for this function, it doesn't really matter. It's just going to be a constant. So the two functions would be that are continuous would be 1 and 3. What is the average rate of change of y with respect to x over the interval of -3, 5 for the function y equals 2x plus 2? So in this case, all I'm doing is finding slope. So we need to find our y's. So in order to find the y's, we're going to plug in the two x values they gave us. So I would get 2 times -3 would be -6 plus 2 would be -4. Minus, plug in the 5, 2 times 5 plus 2 would be 12. And then my x's would be the two x's they gave me here. So -3 minus 5. And let's go ahead and clean this up. So we get -16 divided by -8. So my final answer would simply be 2. So average rate of change, think slope. The last one I worked out for us. It's what is the instantaneous slope of y equals -2x at x equals 2. So this is the equation for instantaneous slope. Okay, you can also hear instantaneous rate of change, equation of the slope of the tangent line. They all mean the same thing. It tells me that take the function, the original function, and plug in an x plus h everywhere there's an x. So that's what we did at the very beginning, okay, right here. Then subtract it from the original function. Now this is going to be a big tip, minus the original function. So my original function was negative. Students always forget to distribute the negative to every term. Next, what I did was find a common denominator so I can combine my numerator into one big fraction. And so here's what I did here, finding a common numerator. I distributed the -2 first, and that's here. Finally, I distributed the negative to each of my terms, and that's my next step. When I distributed the negative, I found that these two terms canceled. And so all I was left with was 2h divided by x times x plus h, all divided by h. So I did the same thing we did previously. I kept the top, changed it to multiplication, and flipped the bottom. So my h's cancel. And so here's what I'm left with. Finally, that I've cleaned up everything, I can go ahead and it tells me the limit as x approaches 0. I can plug in a 0 for my h. And they want to know specifically at x equals 2. So everywhere there's an x, I would plug in a 2. If they don't give me a specific x value for x equals 2, you could just leave your answer as 2 over x squared times the x's. Okay, but in this case, they gave me h because that was the limit, and they also gave me my x's. So I plugged everything in, and our final answer was 1/2. And that's it for the Module 2 review. I hope it was helpful.